We have now studied limits enough that we're ready to return to the questions we started asking at the very beginning of this class. Back in section 2.1, we were talking about derivatives, which were slopes of tangent lines, or instantaneous rates of change. So let's remember what we were talking about. We said lines, with the exception of vertical lines, lines have a slope. That's a number that describes the behavior of that line. Positive if it's going up, negative if it's going down, 0 if it's not doing either, if it's just a horizontal line. And then the absolute value of the slope tells me how steep it is. Now a curve that isn't a line, like this parabola that I've graphed here, doesn't have a slope because it's not doing just one thing. It's going up and then it's going down, and the steepness varies. So curves that are changing what they're doing don't have a slope. But if I look at the curve at just one particular point, so for this example, I'm looking at the curve y equals 3 minus x squared, which is this upside down parabola, and I'm focusing on this point that I'm going to call P. It's the point 1, 2. Okay. At that point, I can draw in a line that captures the behavior of the curve at that point. As I pass through point P, we're going down, and we're going down at about the same steepness as that purple line. If I drew it exactly, we're going down at exactly that rate of steepness as we pass through the point P. So this purple line here we call the tangent line. And that's the line that, if it exists, best approximates the function at that point, so that the slope of the line at that point captures what the parabola is doing at that point. In this case, that it's going down at that rate of steepness. Okay, and we call the slope of the tangent line the derivative. So instead of calling it the slope, it's the derivative. And it's going to be different at different points. I can see at point P, my derivative is going to be negative. If I were over here, I'd have a positive derivative because the function is going up over there. Okay, now, as we were doing that, we said finding the slope of the tangent line. And let's just remind ourselves, I'm usually going to put a subscript of TAN to indicate that we're talking about the tangent line and that that's the derivative. The book often just refers to it as M. That's totally fine. I like the subscript so that I remind myself I'm talking about the slope of the tangent line, because in calculating it, I'm going to need to work with some slopes of some other lines. Because the problem is, I know that slope is just rise over run, but in order to calculate the rise and the run, I need 2 points. And when we're talking about a tangent line, I generally only know 1 point. I know what we call the point of tangency. That's the point on the curve at which we're trying to capture and summarize the behavior of the curve as we pass through that point. So I don't have a second point here. And so what we generally do is we create a different line. We create a secant line. Remember, a secant line is just a line that goes through 2 points on the function. So I'm going to choose P as my first point. I'm going to draw in a point Q. What I'm going to do is I'm going to choose this to be an arbitrary point. So instead of labeling it with numbers, I'm going to label it as x, comma, 3 minus x squared. And then I can draw in the line that goes through those points. So this would be what we call a secant line. And of course, in applications, the slope of a line is just giving us a rate of change. A tangent line is giving us an instantaneous rate of change, and a secant line is giving us an average rate of change. Okay, now I can calculate, this means, the slope of that secant line because I have 2 points. So I can call that the slope of PQ. It's the slope of the line that goes through PQ. Or I could put a subscript of SEC for slope of the secant line. And for that, I'm just using the fact that it's rise over run. So I would say that's going to be the change in y, 3 minus x squared minus 2, over the change in x would be x minus 1. I need to make sure that I subtract in a consistent order. It doesn't matter whether I start my subtraction problems with the coordinates of q and subtract the coordinates of p or vice versa. I find it's generally simpler to start with the more complicated point, which is the one that I've written in terms of variables. Okay, now I can simplify this a little bit because I can combine the 3 and the 2. So I get 1 minus x squared over x minus 1. So that's my secant line. Now I purposely let q be an arbitrary point so that I described it with variables, because we said if we want to try to get the slope of the tangent line, we can approximate it with secant lines, but we tend to get better and better approximations as we choose q, our second point, to get closer and closer and closer to point P. And that was where the notion of a limit first came in, because we wanted to get arbitrarily close to point P, which would be where x was 1, but we can't actually get there. Geometrically, if I get to this point, I no longer have two different points, so that I can't calculate the slope. If I have one point twice, that doesn't give me enough information to determine a line. Algebraically, I can see x can't be 1, because then I would have a 0 in the denominator. So what we wanted to do was we wanted to say, what number do the slopes approach as q gets arbitrarily close to P? And so that's where we get this notion of a limit. Okay, so the slope of the tangent line is going to be the limit. Now I'm moving this point closer to this point. When we're working with functions, we can specify a point by just naming the x values. So this would be as x approaches 1 of the slope of the secant line. So in this case, that's going to be the limit as x approaches 1 of 1 minus x squared over x minus 1. Now if I look at this, I can see I cannot plug in 1, because that would make the bottom go to 0. And that should always be the case. Okay. When you are calculating the slope of a tangent line, you are setting it up so that the bottom of your fraction is going to go to 0, because the bottom of the fraction is your run. But you're also setting it up so that the top of the fraction goes to 0. Because if I'm moving this point closer and closer and closer to this point here, I'm moving both the x and the y values closer and closer together. The rise is going to 0, and the run is going to 0. So when you're setting up a limit that will allow you to calculate the slope of a tangent line, you should always get an indeterminate form of this type, where the top and the bottom are both going to 0. And so then we need to say, how do I evaluate that? Well, in this case, the top and bottom are just polynomials, so I'm going to try to factor. So I can say this is going to be the limit as x goes to 1. 1 minus x squared is just a difference of two squares. That's going to be 1 minus x times 1 plus x, all over, on bottom we have x minus 1. Now, do be careful here. It was 1 minus x squared, not x squared minus 1. So when I factor it, the subtraction problem is 1 minus x. Not exactly the same as x minus 1, but what I can do now is I can say, let's factor out a negative 1 from the top. If I factor out a negative 1 from this factor here, that's going to change the sign of both pieces. So this 1 becomes a negative 1 and a plus x, and then times a 1 plus x over x minus 1. Now this factor here, this negative 1 plus x, that's the same as x minus 1, because the x is positive and the 1 is negative. So this is the limit as x goes to 1 of negative 1. I'm just going to rewrite it so that it looks more familiar. X minus 1 times 1 plus x over x minus 1. I can cancel that. So now we've got the limit as x goes to 1 of negative 1 times 1 plus x. And now I can evaluate this limit by just plugging in 1 for x. So that's negative 1 times 1 plus 1, which is negative 2. So that the slope of the tangent line at that point is just negative 2.